Hello everyone, this is Dr. Webb, and we are up to our last video of the semester. So, here we go. So, on the last video, we started talking about how to find areas under curves. And so this was area we were looking at. And the way that we came up with is, we're taking this total width on the x-axis from 1 to 4. We're going to break it up into a bunch of smaller chunks. And so in this one, there are, I think, 12 different chunks, each one a quarter wide. And then over these subchunks, we're going to pick some height for the function in some way that comes from the function, the value of the function there. So it looks like I'm roughly doing midpoints for each of these. And then using those, that's going to give us a height so that we can then create rectangles. And we like rectangles because it's pretty easy to figure out their area, right? Their area is just going to be the width times the height, right? And so if we can figure out the area of each of these rectangles, we add all these little areas together, that's going to give us our estimate for the total area. Okay, so this is what we talked about in the last video. So if given a function, we're trying to find the area underneath it down to the x-axis, between x equals a to x equals b, and we're going to do this using n rectangles. So this is breaking up a to b into n lengths, and where delta x here is equal to b minus a over n. So this is the width. This is a width of each subinterval, and the f of xk. This is a height for each subrectangle for the little rectangles. And so then when you multiply the height times the width, that gives you an area. Okay, and one bit of notation that we use to simplify this a little bit, to say that we're adding all of these up from x equals 1 to x equals n. We use this bit of notation which is called sigma notation. I talked about this a little bit in our meeting on Wednesday. Sigma notation, sigma is the Greek version of S, and so sigma kind of stands for sum. And so the way that we read this, this right here this is the sum of f of x sub k times delta x. So this right here represents each of these, and it says we are adding this together for all k starting at 1 and going up to n. So the k equals 1 at the bottom says this is where you start the sum, and the n on the top says this is where you stop it. Okay. And so this is our way to give us our estimate for the area. And then natural question is what would we do to make this estimate better? And the easiest thing to do to make it better is to just increase the number of rectangles you have, right? And so our idea is that as n gets bigger, so n is the number of rectangles we get, and so if we're using more rectangles, that's going to make the widths get smaller. So as n gets bigger, this actually means delta x is going to get smaller and go to 0. Our estimates are going to get better. So this naturally brings in the idea, well, how would we get it to the exact area? Well, we'd have to let n just keep getting bigger and bigger and bigger and bigger, right? And so this brings in the idea of taking the limit of this and letting the number of rectangles we use go off to infinity. Okay, and so we set this up as being an area problem, but there's actually a whole lot of different situations where this makes sense. So we thought about this where f of xk represents a height and delta x represents a width. But there's other areas in which this could make sense. And so we could have, say, f of xk. This represents maybe a speed. And then delta x represents a bit of time. And what do you get when you multiply speed times time? Well, speed times time, that gives distance, right? And so you could think about this sum representing you have some speed that's changing over a period of time, and you're trying to figure out the total distance traveled, and so you break it up into little chunks and multiply some speed over that chunk by some little bit of time, and then add those all together to get the total distance. Okay, and so that's just one other example. There's lots and lots where this comes into play. Okay, and so now that we have this limit, it's used in a whole different bunch of ways. Big question is, how do we get it? And so rather than writing this out all the way, mathematicians, in going back to Isaac Newton, really developed this shorthand notation for this limit. And so the idea is this sigma has turned into this elongated S shape. So this looks like an S. It's gotten longer and longer. And then the A, this is the X value that we start at. B is the X value that we end at. And then the delta X has kind of changed into the dx. Sort of in the same sense of when we take the limit using the limit definition of derivative, that the delta x on the bottom turns into a dx. And so we call this the definite integral of f of x from a to b. Okay, so this is just notation. This notation in and of itself, it doesn't really tell us what this limit is, how to get the value that we want out of this, how to get the area, how to get the distance that this represents. So the big question is, how do we do that? And so we want to find the values of these definite integrals to fully answer these area questions. And to help us, we have what's called the fundamental theorem of calculus. This is, in fact, just one part of the fundamental theorem of calculus, but it is the part that we need. And so it says that if we have some continuous function, f of x, from x equals a to x equals b, and then we take any function big f of x, such that when I take the derivative of big f of x, I get little f of x. Well, what's the importance of this big f of x? Well, then, if I want to take the definite integral of little f of x from a to b, all I need to do is take this big f, this function, it can be any function whose derivative is little f, and then I plug in the two endpoints and subtract them from each other, and that gives me the value of the integral. Okay. So what this is saying is that to work out these area problems, all we need to do is find some function whose derivative is equal to the function we're trying to take the area underneath. Okay, and so these big f of x's, because it's sort of you're undoing a derivative, it's called the antiderivative of little f of x. Okay, so let's do an example. So here's our function, f of x equals 3x squared from x equals 2 to x equals 4. So our notation for this is we are starting at x equals 2, going to x equals 4, and then we're doing 3x squared dx. So that's our notation for the definite integral. So now we need to find some big f of x. So we want some big f of x such that when I take the derivative, I get 3x squared. And looking at this, I tried to set this up so this could be something you could kind of come up with, hopefully fairly quickly. What function, when you take the derivative of it, do you get 3x squared? And one such function that works is f of x is x cubed. You can double check by the power rule. When you take the derivative of x cubed, the 3 comes down, and we have 3x squared. And so, using the fundamental theorem of calculus, we can use this x cubed. All we have to do is plug in the right endpoint for cube it and subtract off what happens when we plug in the left endpoint. 2 cubed. So 4 cubed, this is 64. 2 cubed is 8. 64 minus 8 is 56. And there's our actual area underneath this function between these 2 points. Okay. And so one of the important things to note about is that this works for any antiderivative of 3x squared. And so rather than using x cubed, I could use, say, another function whose derivative is 3x squared, is I could do x cubed plus 7. So how is that changing things up here? Let me erase all of this stuff. What happens if I use x cubed plus 7 instead? Well, so then this would turn into 4 cubed plus 7 minus 2 cubed plus 7. And so we'd still have the 4 cubed minus 2 cubed, and then we'd have a 7 minus 7. And so those 7s would still cancel off, and we'd still end up with 56 being our answer. So it doesn't matter, adding something to the end to our big F, it doesn't really change anything. Okay, so let's talk about some rules from definite integrals. So because definite integrals, these are, you can think about these as being sort of the undoing of derivatives. They're kind of a mirror image of a derivative. They're the other side of the coin. One side is derivatives. If you flip it over, you get antiderivatives, you get integrals. And so a lot of these rules that we're going to look at right now, these mirror the rules that we had for derivatives. So same thing as with derivatives. If we have some constant times our function that we're taking our integral of, well, then we can pull that constant out. You know, just like when we had a constant inside a derivative, we could pull that constant out. If we add two functions together and then take the integral, that's the same thing as taking the two integrals and then adding those two together. So that's the same thing as with derivatives. If you're taking the derivative of a sum, you can break it up and you do the two derivatives separately. So this one is different than derivatives. So the idea here is if we want to do the integral from a to b, so we're thinking about this, a to b are happening on the x-axis, and we have our function above. Well, if we want to get this area, we also could stop at some value, say c, in between, and we could get that area by doing it first, doing the integral from a to c, that's the integral from a to c, and then doing the integral from b to c, and adding those together, and that would give me the same thing as doing the integral all at once. And so sometimes this is useful to break an integral up into chunks and do the chunks separately. Last but not least, and so this one is a little bit different, and it gets to the notion of that an integral, the area it gives is it's not just a pure area, it's actually what we call a signed area. There's positive area and negative area involved. And so the idea here is that if we're doing the integral from a to b of our function, but instead of going from left to right, we went from right to left. Well, if you went from right to left, that actually makes the area counting go backwards, right? And so for integrals, we have positive area when our function is above the x-axis and we're moving from left to right. If instead we move right to left, or the function is under the x-axis, in either of these cases, then our area is negative. Okay, so if you do area from right to left, and if you think about this, if you plug this into our formula, this would make all of the delta x's be negative. Then that's the same thing as taking the area from left to right and changing the sign. Okay, so in solving these definite integrals, the name of the game is you can do this so long as you can find an antiderivative. And so this brings in the notion of what's called indefinite integrals. And so what an indefinite integral is it's like a definite integral, but we've just removed the a and b from it. We're just sort of saying what is really what the question that an indefinite integral says is what are the antiderivatives of this function. Okay, and so when we get out of this, we have f of x is one antiderivative, and then this plus c, well, when we take the derivative of any function plus a constant, that constant goes away when we take the derivative. So this disappears when we take the derivative. And so what this really says is that any antiderivative of f of x will look like our one antiderivative plus a constant. Okay, and so for an antiderivative, so for an indefinite integral, what it spits out is an antiderivative plus c represents adding any constant to it. And so really this is representing the whole family of possible antiderivatives for f of x. Okay, so just like we have derivative formulas, we can come up with some indefinite integral formulas. So the first one, we could take derivatives of x to a power, and so if we're integrating x to the n dx, well, it makes a big difference whether n is minus 1 or not, and so this one should say minus 1 right there. So if n is not minus 1, then this is like undoing the power rule. Remember, when we had derivative of x to the n, this gives us x to the n minus 1. And so if we're undoing this, so if I divide both sides by n here, get rid of this n here, and then integrating this, well, the integral cancels that off, and so we get the integral of x to the n minus 1 is x to the n over n. If we rewrite this, convert this n minus 1 to n, then this becomes plus 1. And this works so long as n's not minus 1. And then, if you remember, we did this recently, when you take the derivative of natural log of x, you get 1 over x. And so that means when you take the integral of 1 over x, you get back natural log plus c. Okay. And in fact, this is actually one way to think about defining the natural log, is that it's talking about the area underneath 1 over x. Okay. And just emphasize this is only when n is equal to minus 1. Okay. Another one, we looked at exponential functions. So the integral of e to the x dx is just e to the x plus c, and that's because the derivative of e to the x is e to the x. So this is just the chain rule written out. So this is, the chain rule, it's a pretty straightforward algorithm. When we're taking the derivative, I will say that it's going the other way in terms of integrating. It's pretty hard. It's often pretty hard to identify what f prime and g prime are in a function. So this rule does work, but that doesn't mean that it's easy. So this is true, but not necessarily easy. And then the last thing is, this is just the product rule written out backwards, doing it by integration. I think the important thing to note in this is that the integral of f prime x g prime x dx is not equal to f of x g of x plus c. And that's just because taking the derivative of f of x times g of x does not give you f prime x g prime x. And that's one thing you can always do to check your work. So always to check work, you can always take the derivative afterwards. Take derivative, and you should get back your original function. Okay, so I want to do some quick examples to end up this video, showing you how to do these indefinite integrals using these rules that we saw. Okay, so for the first one, we're integrating e to the x plus x to the e, and so we can break this up into two integrals, e to the x dx plus x to the e dx. So for the first one, the integral of e to the x is just going to give us back e to the x, and then we've got plus c at the end, I'll leave in there. And then for this second one, x to the e, so it's x raised to the power e. Remember, e is just a constant between 2 and 3, a little bit smaller than 2 3/4. And so the power rule says to take the integral of that is it's going to be x to the e. I raise that power plus 1, and then divide by that new power. Okay, and then this integral would have another plus c, but then a constant plus a constant is just another constant. And so we can just leave it as with 1 plus c on the outside. And so that's our answer for the first one. So for the second one, same idea. We're doing this bit by bit. And so rather than writing it out as each separate integrals, I'm just going to take the integral piece by piece. So first we're doing 4 times x to the 5th. So for the 4, I'm not doing an integral, I'm actually writing out the answer. So the 4 I can leave behind and then apply the power rule. So x to the 5th, I raise the power by 1, I get x to the 6th divided by 6, plus the integral of x squared x, 2 plus 1 is 3, divided by 3, plus a constant 3. So I'm going to think about 3 as being 3 times x to the 0. And so then I can use the power rule on it. And so 0 plus 1 gives me 1. So 3x, and then divided by 1 just leaves it the same. Plus, now I have 2 over x. So this is the one time when the power rule is different, because I'm just dividing by 1 power of x. So this is the power of x here really is minus 1. And so that's when I get, I'll write it down here, natural log of x. And then for the last one, my power of x here is really minus 4. And so I'd have minus 3. So if I have minus 4, adding 1 to that would give me minus 3. And then divide by the new power, minus 3. And so minus 3 over minus 3, that would cancel off. Okay. And then I have a plus c at the end. And so our final answer for this one is 4 times x to the 6 over 6 plus x cubed over 3 plus 3x plus natural log of x plus x to the minus 3 plus c. Okay, so for this last one, this one is a tricky one. I'm doing this to illustrate kind of a bit of how the chain rule, undoing the chain rule works. Okay, so looking at this, I've got a square root going on, but it's in the bottom, and I have 2 on the outside. And so if I let my f prime, my f prime, not f to the minus 1, my derivative of f be 1 over 2 square root of x. And then if I have my g be 3x plus 1, well then my g prime is equal to 3. And so when I look at this, I've got my 3x plus 1 right there. I've got a 3 there, corresponding to that 3 there. And then this is all being plugged into 1 over 2 square root of x. Well, which function has derivative 1 over 2 square root of x? Well, that would be square root of x. So this is of the form integral f prime with g of x plugged in times g prime of x dx. And so on the other side, this is going to equal f of x, f with g of x plugged in, plus c. And so my f is, take the square root, my g is 3x plus 1, and then I add c at the end to give me my answer. Different than that answer. Okay. And if you don't believe me that this works, take the derivative of the square root of 3x plus 1. And if you get back 3 over 2 times the square root of 3x plus 1, then it worked perfectly fine. Okay, so here are our last practice problems for the term. So first, I have these 3 indefinite integrals for you to do. Remember to do the plus c at the end. For the third one, where it's all written in terms of roots, remember to think about the roots as powers, and then use the power rule to do that. And then for the last one, has an area under the curve problem, so it's really asking you to write this as a definite integral, and then use the rules of integration that we saw to get a value for this. Okay, I will see you Friday morning.